Hello and welcome to another presentation, this time on the compound angle formulae and the double angle formulae. Now, the compound angle formulae are given in the formula books, so that's quite nice for the students, whereas the double angle formulae aren't, but the double angle formulae are very easy to derive from the compound angle formulae. I do ask for a proof of the compound angle formulae in this module using the rectangle and the triangle within the rectangle. There are actually many other ways, quite simple ways as well, of proving the compound angle formulae. I'll leave it up to you as an exercise to derive them in a different way if you like, but I quite like the way with the rectangle, which you'll need to do to complete this module. So we'll leave it at that and we'll take the proof as read. Now, why use the compound angle formulae? Well, they can be used to solve all sorts of problems, and principally I like introducing them because you can use them to derive the double angle formulae. But let's use them for a different reason. Let's say we wanted to find sine of 75 degrees as an exact value. Well, we could do that because we could write 75 as 45 plus 30. And as we already know what sine of 45 and cos of 45 and sine of 30 and cos of 30 is, we can now work it out, because we'd have sine of 45 cos 30 plus cos of 45 sine of 30. And that would give us 1 over root 2 times root 3 over 2 plus 1 over root 2 times a half, which, if we factorise out the 1 over 2 root 2, we'll be left with root 3 plus 1. And so we could in fact write that as root 3 plus 1 over 2 root 2. So that's the first reason why you might need to use compound angle formulae. It's quite helpful for expressing angles in their exact form. Now, the biggest reason why I like the compound angle formulae, I like to introduce it, is really to prove the double angle formulae, which tends to be more prominent in the A2 syllabus. You use the double angle formulae for lots and lots of useful steps in, for example, integration. If you have to integrate sine squared or cos squared x, then double angle formulae is indeed very, very handy. So they serve more of a purpose really than the compound angle formulae. That said, questions do come up on the compound angle formulae, but it tends to be the double angle formulae which comes up more. Okay, so let's start with a double angle formulae. If I want to find out what sine 2 theta is, then I could write it as sine theta plus theta. And as I know now that that's the same as sine theta cos theta plus cos theta sine theta, and as I've really written the same thing down twice there, I can now deduce that sine 2 theta is the same as 2 sine theta cos theta. Likewise, I could do the same thing for cos 2 theta and rewrite it as cos theta plus cos theta, cos theta plus theta, I apologise for that, and that gives me cos theta now minus sine theta, and we end up with the classic formula for cos 2 theta, which is cos squared theta minus sine squared theta, which can of course be written as, because that's the same as 1 minus sine squared theta, 1 minus 2 sine squared theta, or because that is the same as 1 minus cos squared theta, 2 cos squared theta minus 1. And we've derived all of the double angle formulae for sine and cos. Likewise, we could do the same for tan, with tan's rather awkward compound angle formulae. The tan compound angle formulae is a bit more ungovernly. It's just a little bit irritating to work with sometimes. Now let's go through a few questions where we need the double angle formulae or need some facts about the double angle formulae. Okay, I'm going to start by proving the following identity. 1 minus tan squared theta over 1 plus tan squared theta is identical to cos 2 theta. Now, when I'm proving identities, the advice I always give to students is it's almost always best to go from the more complex to the more simple. And that's because we simplify a lot in maths, but I can't recall ever complexifying anyway. It just seems to be more difficult to go from the simple to the complex, and always easier to go from the complex to the simple. Because you could work with the left-hand side or the right-hand side here, but I'm going to work with the left-hand side. And I do like my students to write left-hand side equals something else, equals something else, and then eventually end up with the right-hand side. So obviously on the left-hand side, the first thing we've got is 1 minus tan squared theta over 1 plus tan squared theta. Now there's lots of things we might think about doing here. For example, maybe difference of two squares on the top, because we've got an a squared minus a b squared there, with a as 1 and b as tan theta. Sadly, I don't think that's going to yield us any fruit, but we could write tan squared as sine squared over cos squared, and that's what I'm going to do. Over 1 plus sine squared over cos squared. The reason why we might choose to do this is because then we could multiply top and bottom by cos squared theta, yielding cos squared minus sine squared on the top, but cos squared plus sine squared on the bottom. Now that is very, very nice, of course, because cos squared plus sine squared is simply 1, and cos squared minus sine squared, we discovered in the last slide that that is exactly the same as what we're looking for, cos 2 theta, which is the right hand side, and that completes our proof of that trigonometric identity. Double angle formulae are frequently in trigonometric identities, and I always say to my students, if there's a double angle in there, you'll need to use double angle formulae at some point. You just cannot avoid it, unless everything's a double angle, in which case but you possibly could avoid it. But you know, if there's some double angles and some single angles, you're going to need the double angle formulae. Okay, lastly, let's look at solving an equation involving a double angle formulae. Now this is exactly what I was just talking about. Because there's a double angle in there and a single angle, you've got no choice but to use double angle formulae. Now with cos 2 theta, you've actually got 3 different formulae you could choose from. There's a very natural choice here though, and that would be to use 2 cos squared theta minus 1. That's because that would put everything in terms of cos theta. So 2 times 2 cos squared theta minus 1 equals 1 plus cos theta. Now, as I've mentioned before, once you've got them all in terms of single angles, it might be better to write it as just c squared minus 2 equals 1 plus c. It just makes it a bit clearer. That gives us 4c squared minus c minus 3 equals 0. Factorise, and we're very fortunate that this one does factorise. They sometimes, very occasionally, give you one which doesn't factorise in the exam, but that's quite unusual. That gives us 4c plus 3 in one bracket and c minus 1 in the other. And hence cos theta is minus 3/4, or cos theta is positive 1. Now, cos theta is one I'll deal with first because it's easier. I can just see the cos curve in my head, and that happens at 0 and 360. This one I will need a calculator for, and it comes to inverse cos of minus 0.75 is 138.6, and the rule of thumb for cos is 360 minus that answer, and that gives us 221.4. You may plug any of these back in and you will see that the equation is solved. I always encourage students to do that, because if they genuinely have solved an equation, they should be able to tell in the exam hall whether they've solved it correctly. Okay, that completes this mini presentation on compound angle and double angle formulae. I hope you enjoyed it, and yeah, I will speak to you again in the next one. Bye bye.